We next discuss entanglement purification. In entanglement purification, we use multiple entangled states with lower fidelity to create a single entangled state with higher fidelity. Purification protocols need a certain level of fidelity for each used entangled state, and so we need to make sure that fidelity has not degraded too much by the time we do purification. Qubits are fragile in the quality of their quantum information. In this case, the fidelity of the entanglement decays due to noise. Noise refers to many different factors that can cause loss of quantum information, such as environmental factors, manufacturing defects on components, natural physical processes, etc. To combat noise and keep fidelity at a high enough level so that we can even do purification, and eventually so that we can run end-user applications, we must use purification many times throughout the entanglement distribution process. Again, like with EEG, there are many different purification protocols that we can use. We will be using a controlled NOT or C0 gate in our purification protocol, so we'll first introduce it here. C0 gates are essential components of gate-based quantum computers. They are often used to entangle and disentangle quantum states in quantum computing algorithms. However, they can also be used in quantum networks, as we will see. C0 gates operate on 2 qubits. The C0 gate flips the target qubit if and only if the control qubit is a 1. The graphic below shows a few different representations of C0 gates. It's important to note when it comes to optical components, so that is using photonic qubits and photonic systems, our C0 gate will be probabilistic. We will use a relatively simple but still illustrative example of a purification protocol. Alice and Bob share 2 entangled pairs. Psi1 is the entangled pair whose fidelity they are trying to increase, and Psi2 is the entangled pair they are using to help accomplish this. Alice and Bob first apply C0 gates on their 2 qubits respectively, with the control qubit being from Psi1 and the target qubit being from Psi2. Alice and Bob next measure their half of the pair of qubits from Psi2 and compare the results. If they get the same result, then the distillation is considered a success and they will keep Psi1. The fidelity of Psi1 will be at least as high, but often higher than as before. If they get different results, then the distillation or purification is considered a failure and they will discard Psi1 and try again. We will leave the math behind why this protocol works for another time.